This video, we're going to carry on with our discussion of normalization, and we're going to move into what's called the second normal form. Right. So we talked previously about that originally we were doing normalization, we had some sample data, and for instance, it might have had some multi-valued fields. So we flattened the file, and that gave us the that each cell was a single valued and unique, but that process of flattening the file, but it introduced a lot of redundancy. And we talked about the problem with redundancy, especially say in like an update anomaly that if you change something, you're going to have to change it many places. So you're going to be storing it in many places. If you're going to update it, you're going to have to change it in many places. And so we talked about splitting the table. And now we would like to consider more formally, like, what's the process for figuring out how the table should be split. And so we start to talk about the concept of functional dependence. So we have this table, the sample data provided a number of columns, of fields, and now we'd like to know how do they depend on each other? How does one field depend on another? And those dependencies can inform us about how to split up the table. Okay, so we have a bunch of like sample records, and you have to look at your sample data, but also sometimes think a little bit beyond, you know, uh, you know, to imagine beyond the data in the sample data sometimes. But we want to know, does like one field depend on another? So if I know A, does it tell me B? So if knowing A tells me, then I can determine what B is, then we would say that B functionally dependent on A. Okay. And we're imagining in our previous example when we had like our original table had information about people who were voicing characters in the Simpsons show, then our flattened table had information both about uh, characters and about real people. And so we imagined that there must be some ultimately some key that each row uh, had to have uh, s- something that depended on the person and something that depended on the character. And so our fields can be our keys, our thing that you uniquely identify each row are often in that case composite. And then we want to know like what depends just on one part, what depends on another part. All right. So here's just some concepts of functionally dependent. I might have um, an age, uh, an age category, date of birth. Then such a thing would be called like derived, depending on what you have first. Like if I know the date of birth, then I can derive an age, or I can derive an age category. Um, doesn't always work the other way. If I know the age, I can get the age category, but if I know the age category, I can't get the age. And same thing for the date of birth. With the date of birth, I can get the age, but with the age, I can't get the date of birth unless I know the age down to, I don't know, days and seconds or something. Um, but in this case, you would say it's functionally dependent. Now, in a situation like this, you might not store something that you can completely derive. Um, but there are other versions of functionally dependent. But this is like our first example of clear functional dependence. If I can completely derive one thing from the other, it depends how difficult something is to derive. So if something's quite complicated to derive, then you might store both values, or you might only store the one from which you can determine the other. But whichever way, this then one is functionally dependent on the other. Knowing the date of birth, I can determine the age. Knowing the date of birth, I can determine the age category. Okay. Now I can say that date of birth is functionally dependent on the social security number. Well, how's that? There's no like mathematical relationship that says like if I know your date of birth, I can calculate your social security number. Or if I know your social security number, I can calculate your date of birth. Um, but a social security number in the US determines identifies a person or should identify uniquely a person. And then that person has a date of birth. So in that sense of being able to just look it up, then being able to look up uh, their social security number then identifies the person, and then knowing the person, I can look up their date of birth. So if I have that information, one is if I have both pieces of information, one is dependent on the other. The social security number, the birth date is dependent on the social security number, not vice versa. Two people might have the same date of birth, but they won't have the same social security number. So the social security number will determine the date of birth, but not the other way around. Okay. Now, if we have a primary key, then everything depends on the primary key. That was we said that that's the role of the primary key, is that it picks out each row can be identified by the primary key. So everything in that row thus is dependent on the primary key. And so, but we're imagining these like complicated tables. We have this sample data and we have these complicated tables where like things are just all mashed together. And we are imagining a composite key that's going to be important in what we're doing. At least for now, we're imagining a composite key, and then that will be part of our sort of breaking things down process. So, so everything depends on the primary key. If the primary key is single valued, that's not going to tell us much. But if the primary key is a composite key, then that's going to get us somewhere in this process. Okay. So let's imagine that we have this. Now, if you can choose primary keys, and so you might say, well, I would never choose this composite primary key. And then, okay, that's why we have like a third normal form. But let's just imagine we do have a composite key, and then let's work with that to get to the second normal form. And then another time we will worry about third normal form. Okay. So now we have a primary key. We're going to imagine then it's composite, that there's two properties combined that are primary key, that each row is unique with this combination of two fields or three fields. So we have a composite key. And then if we have a composite key, we can start to ask about partial dependencies. Does do I have everything depends on the primary key, but are there things that depend only on part of the primary key? Do we have any partial dependencies? So let's imagine I have information about uh, people, directors directing movies. Okay, so I have some table with this information, and I might have some ID that identifies the movie and some ID that identifies the director. And then I have all the other information, the title of the movie, the type of the movie, description of the movie. I don't know, it's year of release. That's not here, but it could be the director's first name, the director's last name, the director's date of birth, country of origin, all sorts of things we could have. And now we have a composite key. then if we know the movie and the director, then we can identify our row. So we had uh, some directors that had multiple movies, some movies that had multiple directors, but we flattened our files, and now we have uh, the combination of the movie ID and the director ID was unique and is serving as our composite key. Okay. Now we can pick out the parts that depended only on the movie ID, the movie title, the movie type, the movie description. These were all just really just part of the movie and therefore depend just on the movie ID. But the movie ID is only part of the primary key of this table that we started with. And the director first name and the director last name and the director date of birth, that all just depends on the director ID. So we have things that depend on just part of our composite primary key. Okay. So things that depend on just one key can be split off. So we can split off all the things that depend just on the movie, creating a movie table. We can peel off everything that just depends on the director and make a director table. And then if there's anything left that depends on both, then that will sort of stay in the original table. So we had this one table that was movies and directors and all that information, and we're sort of splitting off movie and we're splitting off director, and we may have things that are left that depended on both the movie and the director. Okay, so one gets movie, which has a movie ID and the movie title and the movie type and the movie description. We might have the director, which has the director ID and the director first name and last name and date of birth. And then we might have this combination of movie ID and director ID in left over still in the original table. Now it depends on we always talk about relationships and we say now, um, a director makes many movies. And then a movie, now we have to ask the question the other way around. A movie is made by, and I'm imagining here many directors. So that would make the movie to director a many to many relationship. So if a movie can have more than one director, then it's a many to many relationship. And then that movie director, the movie ID, director ID, stays in the sort of original table where they were together. Now, if you said that a movie just has one director, then then the director ID is dependent on the movie. Yeah, so I would. So if a movie has only one director, then there's a dependence between them, between those two IDs. Um, but that was that was the one to that would be a one to many relationship, and then we'd expect the director ID to be in the movie table as a foreign key. But if it's a many to many relationship, then there is no dependence of like one ID on the other, and so those two IDs stay in the original table. So so this idea of normalization brings back that same idea of do we or don't we need a bridge table depending on the is it a many one to many relationship or a many to many relationship? I'm imagining here a many to many relationship. So here's me having Googled some time ago the uh, some movies that have multiple directors. So just to say that that exists. But in our Simpsons example, we imagined that a character was voiced by one person. In the long run of the show, I'm not sure that's completely true, but that's how we imagined it when we were talking about that thing. And so then the uh, when we have the character, uh, the person who voices that uh, is dependent on the character. So if I know the character, I can determine um, the person who voiced it. And so then that would split into two tables because it's a one to many relationship. But the director to movies, as we imagined, many to many, then we retained a table with the composite key in it because that became our bridge table. And so now we have arrived at our second normal form. So we flattened the table, moved into our first normal form, and that introduced some redundancy. We identified a primary key. If that primary key was composite, then we can imagine there would be some partial dependencies, things, fields that depended on only a part of the composite key. And if we split up tables based on things that are only dependent on part of the primary key, then we have arrived at what we call the second normal form. And as we've hinted, this was dependent on your choice of key. And so it shouldn't be, we shouldn't be stuck uh, that, if you introduced a key that wasn't composite, we shouldn't be stuck. We would be stuck in terms of second normal form. So there is third normal form and even higher. We will talk about them another time, but imagine that we had a composite key and we had some partial dependencies, then this idea of the second normal form gives us some idea of how to split apart our table and yet maintain our relationship. So we have this sort of lossless join. We can get back to the original table. That's important. And that's it for this. More on normalization another time. Thanks for your attention.